Hi, this is the biostatistics webcast, and I thought that it would seem scary, so I made flower slides. Hopefully that will help. There's going to be some math in this. Some of the math you will have to know how to do. Most of it, I just want you to see it so that you can be exposed to it and sort of understand vaguely what goes into the different formulas. But I will be very clear if you actually need to know how to calculate something. So we're going to talk about different types of variables and how they are compared statistically. We're going to show how to perform simple comparisons with computations, standard deviations, confidence intervals. I'll show you how to use statistical tests to compare different types of variables in different ways and match those tests to different types of studies. And then I'll briefly discuss how multivariable comparisons are performed. You won't be expected, but I just want you to understand how those types of comparisons can control for confounding, which we talked about theoretically in the other webcast, and I said I would talk about how it was dealt with statistically here. Okay, so there's several different types of variables in studies, and this is something you may have been exposed to already, but I'm just going to say it again. The first type is a continuous variable. In those cases, the variable is measured along a number line without any breaks. And so some good examples are weight and age. A continuous variable means that it goes 1, 2, 3, 4, 5, and 2 is worth twice as much as 1, and 4 is worth twice as much as 2, and 2.5 is halfway between 2 and 3, right? That's all intuitive. An ordinal variable, though, is a variable that's measured with sequential numbers, but it's not continuous. And so the best example is, you know, those surveys that you take where it says, it has a statement like, I really love biostatistics. 1, strongly disagree. 2, disagree. 3, neutral. 4, agree. 5, strongly agree, right? Those are called Likert type scales. They're named after some guy named Likert. And those scales have numbers in them, 1, 2, 3, 4, 5, where 1 is the lowest and 5 is the highest, or in this case on the slide, it's 1 through 4. But in these cases, 2 is not worth twice as much as 1, and 1.5 is like not really a value, so it's not quite the same as a continuous variable, and it's just helpful to understand the difference. Categorical variables are also quite commonly used. It's a variable where there are a couple of different values, but they're not numerically related to each other, like gender, male, female, or pet owners, people who own cats, people who own dogs, people who have no pets at all. Region of the country, Northeast, Midwest, West, South, etc. These variables are sometimes referred to as dichotomous, meaning they have 2 categories, or more than 2 categories. So if you hear people say dichotomous, usually it means that it's a variable that's been made into 2 categories. And in the case of age, which is on the slide, sometimes it's a continuous variable where they drew a line and said, everyone under this number is in category 1 and everybody over this number is in category 2. So you can always turn a continuous variable into a categorical variable, but you can't go the other way. I want to talk for a minute about mean, median, and mode. Mean is the average. I know you guys know this, I'm just going to say it again, which is the sum of all the results divided by the number of the results that were counted. Median is the number in the middle after all the measurements have been put in order numerically, so laid out from the smallest to the biggest. It's just the number that happens to be in the middle. And the mode is the number that shows up most frequently in the list of the numbers. So I'm going to show you an example of this. So here's an example with mean, median, and mode. Say we have a first-year medical school class, a pretend class, of course, that only has 9 students in it. That's how you know it's pretend. And we give a test, an exam, and the scores range very widely from 45 to 98. See, I laid them out for you end to end. So we're going to do mean, median, and mode on this data. The mean is just you add them all up and divide by 9, which is how many there are. And I did the math for you at 77.3. The median is the number that's in the middle when you lay them all out lowest to highest, right? So the number in the middle is the 5th number, and that is 82. And the mode is the number that occurs most frequently in the list, and in this case 82 occurs 3 times, so that is the mode. The main point about this is just, first of all, we hardly ever use the mode. I've never actually heard anyone use the word mode, it's just, except when they're teaching the slide on mean, median, and mode. So the likelihood is that you won't use it either. Mean and median are not the same number, and they don't mean the same thing. Sometimes I think in the press or when people are talking casually, they interchange the words mean and median, but they don't actually mean the same thing. And in many cases, the mean will be different than the median if there are some outlying scores, either low or high. So in this case, the 45 is significantly below the other numbers, and that drags the mean down where the median is 82. And so that's just worth remembering. All right, so what is a standard deviation? I want you guys, this is something I actually want you to understand, although I don't think I'll ask you to calculate it because it's a long calculation, but I want you to just take you through a calculation. It's a measure of how widely dispersed the data are around the mean. So a large standard deviation means that the data are widely dispersed, which I'll show you in the next slide. It gives you a sense of how much variation there was in the sample population. Usually, 2 standard deviations from the mean in either direction contains 95% of the values in the sample population. And how it's calculated is we calculate the difference of each data point from the mean and square each difference. And then you take the mean of those values, take the square root of the mean, and that's the standard deviation. I'll take you through it in a minute. This is helpful not only in research, but in many clinical tests like lab tests. 2 standard deviations from the mean is considered sort of the normal value. So like if you are looking at someone's white blood count, right, and it's 8, say, and the normal range is considered to be 4 to 11. I'm sort of making this up, but I think that's about what it is. I'm not making it up, I just don't remember it exactly. So if that were the case, then 4 to 11 means that that's 2 standard deviations below the mean to 2 standard deviations above the mean. And that's sort of how we decide what's quote unquote normal. It doesn't necessarily mean that there aren't people in the population whose white blood count is normal and it's slightly outside 4 to 11. But we use that to sort of ballpark, you know, most of the values should be within this range. Okay, so here's 2 collections of data points. The data points are purple and the means are green. Now you can see that they have the same mean, but in the top example, the data points are more widely dispersed and the standard deviation will be larger. So we're going to calculate a standard deviation. We have 10 values. I made these values very small because there's a lot of adding and subtracting, and you know that I don't like to do that, so I wanted to make it easy to follow. So say we have 10 values and I laid them out there. So the mean, which we know how to do, is 5.9. I rounded it up to 6 to make things easier. So the mean is 6. The differences from the mean are, you basically take each one of those numbers and, you know, see what its difference is from the mean. So 6 minus 3, 6 minus 4, 6 minus 4, etc. Then you take those differences and you square them. So here what I did is I just went through, I found all the differences from the mean and I squared them. And then I added up all the squares and took the mean of the squares, which is 3.7. And then you take the square root of that number, which is 1.9. And so the mean is 6 and the standard deviation is 1.9. I'm not going to ask you to do this. I just want you to understand how it's done. So means and confidence intervals, we talked about this a little bit with the 2 standard deviations. Sometimes the territory covered by 2 standard deviations is referred to as the 95% confidence interval. And that basically means that it contains 95% of the values in the sample population. In particular, when studies report odds ratios, so in some types of studies lend themselves to an odds ratio as the final result, the odds ratio is usually reported with a 95% confidence interval. So for example, if you did a study looking at the risk of stroke in people who smoke, say, and you found that people who smoked had 1.8 times the risk of stroke compared with people who don't smoke, that's an odds ratio. The 1.8 is an odds ratio. It would be reported with parentheses next to it with a 95% confidence interval. It would say 1.8 parentheses 1.3 comma 2.5. And what that means is that 1.3 is 2 standard deviations below, and 2.5, I think I said, is 2 standard deviations above. We'll come back to that later in this, but I just wanted you to sort of hear that. It's important to have a sense of how dispersed the data are in order to know what the mean represents. And we talked about that a little bit with that graphical example. So most of what we try to show in statistics is whether the difference between 2 variables or 2 groups or 2 data points is greater than a difference that you might have observed by chance. So you can imagine that if you were, for example, comparing two means and there was a huge standard deviation in both groups, that there might be a lot of overlap amongst the data points. And then you might start to argue, well, are these two means really different, or might this have been observed by chance because these two groups have a lot of overlap between their data points? And so what statistical significance tells you is it is actually a greater difference than would be observed by chance. So this is just a little drawing that I did showing normally distributed data. And you can see that the two little lines are standard deviations, one standard deviation and then two standard deviations. And so two standard deviations on either side of the mean contains 95% of the values. I showed this to you for two reasons, just to graphically represent the 95% confidence interval, but also to say that all of the statistical tests that I'm going to show you in this lecture are only applicable to data that are normally distributed. And data that are not normally distributed, we can talk about that more in class. It's not something that you need to know for this class, but there are some collections of data where the data points don't lay themselves out in this way. And it's usually in studies that are very small. And so there are other kinds of statistical tests that you do to deal with that, which we won't talk about. I mean, we can talk about them. They're not taboo, but you don't need to know them for this class. All right, so the important thing about this is when you study relationships in epidemiology between exposures and outcomes, you want to know things about the relationships that you see. And really what you want to know is sort of, are they real, right? And that gets answered in a couple of different ways. One is, are they substantive? I don't say significant for this because significant really means one specific thing. But substantive means, is it a big difference, or is it a big enough difference to be clinically meaningful? And then the second thing you need to know is, are they statistically significant? Meaning, if we repeated this experiment several times, would we get the same answer, or was it just a fluke? And then the other thing you need to know is, we talked about this a little bit in the other webcast, is what is the real relationship between A and B after controlling for confounders? And this is called multivariate analysis, and we'll talk about it a little bit later in this study. So when you test a hypothesis, there's two terms that you should know. One is the null hypothesis, and the other is the alternative hypothesis. This is sort of like clunky statistics language, but you should know it because the real statistics people use it. So the null hypothesis is there's no difference between the two groups in this study, or we could not find a difference. The alternative hypothesis is there appears to be a difference, and we are rejecting the null hypothesis. So you go into the study sort of mathematically assuming that the null hypothesis is probably true, and so the threshold to reject the null hypothesis is rather high. And that's good from a math perspective because it means that you're not likely to run around finding significant results in all these studies and creating chaos in the research world as a result. So say you're doing a study to see whether statin use, those are cholesterol-lowering drugs, is associated with a lower risk of coronary artery disease, or CAD. By the way, it is. But this is a made-up study. So you have two groups of patients, one that took statins, which is group 1, and one that didn't, which is group 2. So your alternative hypothesis is group 1 will have a lower risk of CAD than group 2, right? So suppose you're counting CAD as a continuous variable, as events per year. And group 1's mean was 32.9 events per year, and group 2 had 33.3 events per year. Those are pretty close. So the question is that really a difference? And so the null hypothesis is group 1 and group 2 do not have a different risk of CAD, meaning 32.9 is essentially the same or close enough to 33.3 that it doesn't really make a difference. If you find that there is a statistically significant difference between 32.9 and 33.3, then you have rejected the null hypothesis. The two numbers are still pretty close, and so whether it's a clinically meaningful difference is sort of another story, and that's not a question for today. Today is all about the math. So p-values, the main way that statisticians evaluate whether something is statistically significant is they do statistical tests on it, and those statistical tests result in a p-value, which we'll talk about more in a few slides. The cutoff for the p-value, meaning is it statistically significant or not, is usually 0.05, meaning if the p is less than 0.05, it is statistically significant. Now, in some studies, you can change the cutoff to like 0.1 or something, but conventionally 0.05 is used. So in this study, if you found that group 1's rate of CAD was 32.9 and group 2's was 33.3, like we said, and the p-value was 0.0026, then those results are statistically significant, meaning you rejected the null hypothesis and you found that the patients taking statins actually did have a lower risk of CAD. But if you found that group 1's rate of CAD was 32.9 and group 2's was 33.3 and the p-value was 0.384, which is clearly larger than 0.05, then those results are not statistically significant, and you did not have sufficient evidence to reject the null hypothesis. This is not the same as saying the two groups are exactly the same. That's actually kind of a different statistical test that we're not going to get into in this class, unless somebody really wants to. What it just means is we cannot be sure. We do not have enough evidence to say that the two groups are really different. And usually, the difference between finding a statistically significant result and a not statistically significant result, like for example with these numbers, would be sample size and the standard deviation. So my guess would be, in the first example where it is statistically significant, the sample size was very large in the two groups and the standard deviation was very small. So the difference between those two numbers, even though it's a small difference, was thought to be bigger than a difference that would be observed by chance. So what does it mean to say that the p-value is less than 0.5? I just want to make this clear because a lot of people don't quite have this right in their head. What it means is if we repeated this experiment 100 times with this sample population or one just like it, then 95 times out of 100 we would reject the null hypothesis and find the result that we found here. And that is considered to be very robust. And most math people and statisticians are really happy with that and say, okay, it's real, it's statistically significant. What it does not mean, but a lot of people think it means, is that the true value in the real population, not the sample population, is 95% likely to be the same as what we found in our sample. That's not what it means. The p-value is only a comment about the study sample and saying if we repeated this study multiple times with a sample just like this one or the same sample, it doesn't apply to the population at large. So now we're going to talk a little bit about statistical analyses and how to compare different variables. When you analyze data for a study, the way you tell whether differences are statistically significant is to apply statistical testing. The test depends on which type of variable is being analyzed. Remember at the beginning of this webcast we talked about types of variables. And each test result correlates with a p-value. So you get a test result and then you look up in a table or on the computer what p-value it correlates with. And in general, the statistical tests, the higher the number of the statistical tests, the more likely it is to correlate with a low p-value. So higher is better. And the p-values tells you whether it's statistically significant. So the plan for the next several slides is I'm going to show you some common types of tests, briefly discuss how you get the result, like what's in each formula. You will not ever have to calculate these things. The statisticians even use the computer for this, but I think it's important for you to see like what's in the numerator and what's in the denominator, so you know what kinds of ingredients go into making things more and less likely to be statistically significant. So this is just watch this, don't stress about the formulas, but just get a general sense of what kinds of things make it more and less likely to be significant. And there is a summary of this in your syllabus as well. So we're going to talk about t-tests, chi-square tests, analysis of variance or ANOVA, and linear and logistic regression. So t-tests, this is probably the easiest one to explain and it's very commonly used. It's used to compare the means of two continuous variables. For example, say you want to compare test scores on our exam between people who attended class and people who did not attend class. I'm not saying that I feel one way or the other about that, but let's just see if they do differently. There are two kinds of t-tests you can do, paired and independent. We're going to talk about independent t-tests right now, but just so you know, there is this thing called a paired t-test, which compares two means from related groups. Most commonly, it's pre and post values in the same group. And the reason that it's a different test is just that if the two groups are related or the same, their values are a little bit more likely to be correlated. But for this, we're going to look at independent t-tests because it's two different groups of students, the ones who came to class and the ones who didn't. So The results that we get from this t-score, which I'll show you in a minute, will be used to generate a p-value. And so the results, when we say them in English, will sound something like this. Group 1, students who attended class, had a mean score of 86 on the exam, where Group 2, students who did not attend class, had a mean score of 84, and the p was less than 0.05. That means that the 2-point difference between the two groups was a statistically significant difference. Whether it's a difference that matters is something that you can discuss amongst yourselves. It's not a very big difference. Or we might find that it's not statistically significant. And so the question is, what would be the difference? What would change the t-test one way or the other? So this is the formula for the t-test. Again, just don't stress about it. Just look at it and sort of let me talk you through it. X is the mean of each group, so that's in the numerator. N is the number in each group, so the number of observations. And that's in the denominator, but it's in the denominator of the denominator. So it's really in the numerator. So basically, if the difference between the means is a large number, then that will make the t-test, the t-value go up. And if the number in each group, N1 or N2, is a large number, then that will make the t-test go up. And S is an estimate of the standard deviation in each group. So if S is a large number, that will make the t-test go down because it's in the denominator, right? So chi-square tests. By the way, I didn't actually calculate a t-test because it's such an enormous pain in the butt to do it, but I just wanted to show you the formula. So chi-square tests are used to compare percentages between two dichotomous variables. Dichotomous variables are things like male, female, or, well, let's see what we have here. For example, you want to compare the incidence of heart attack, MI, in two groups of patients. One group received cholesterol-lowering medicine and one did not. And so we want to know what percentage of people had an MI in each group. Chi-square tests are also reported with a p-value, and you find it in a table or it's generated through a statistical program. But basically, if your chi-square value is high, then your p-value is more likely to be statistically significant. So let's say 14% of the people in the medication group had MIs in the time period specified. Say it was, a year or 5 years or something. And 16% of the people in the other group did. So the question is that 2% difference between the two groups statistically significant or not? And I'm going to show you how we get the data. So the chi-square is the sum, that's what that E thing is, of the observed minus expected squared over the expected. And what that is for each cell in the table, so suppose, again, you have a table, a 2x2 table, took cholesterol medicine, didn't take cholesterol medicine, had an MI, didn't have an MI, right? The expected value for each cell on the table is the value for didn't take the medicine, right? So observed minus expected is any difference that you find in the group that got the intervention. And then you square that and divide it by the expected, and you add them all up for each cell on the table. So there would be 4 cells in this table. Then that number is compared in a table to expected values for the number of degrees of freedom on the test. This is a concept that I always have trouble with, a lot of people do, but basically degrees of freedom has to do with how many different things are you looking at in your table. And in this case, the degrees of freedom would be 1 because you have 2 rows and 2 columns. So 2 minus 1, which is 1, times 2 minus 1, which is 1. So that's 1. So it's a 2x2 table. But if you were looking at a 6x6 table, then your degrees of freedom would be different, and you would look at a different number. And then whatever you get in the table, the chi-square number in the table, is used to generate a p-value. And that tells you whether it's statistically significant. So basically the take-home from this is that the bigger difference there is between observed and expected in the table, then the more likely it is to be statistically significant. You will see in this formula that there is no standard deviation and there is no number of observations like there is in the t-test. So those things do not directly contribute to the chi-square number in the same way that they do for the t-test. So analysis of variance is the test that you do when you, for example, want to do a t-test, but you have more than 2 groups. So remember, with the t-test, we looked at students who came to class and students who didn't come to class. With the analysis of variance, you can say, okay, let's go back to the same example. Our outcome is a continuous variable. It's the score on the exam. But for our purposes now, we're interested in, let's look at students who came to class every single time compared with students who came to like more than 50% of the classes to students who came to less than 50% of the classes. So we want to see is there sort of a dose response thing where the more often you're in class, the better you do. Again, I'm not sure that this is 100% true, and you're speaking to someone who, to be perfectly honest, skipped a lot of class in medical school, so I'm not sure that it's true, but I just need an example for this class. So let's say we split the group into 3 groups instead of 2. So group 1, the students who came all the time, had a mean score of 89.4, group 2 had a mean score of 87.1, and group 3 had a mean score of 86.1. Not a very big difference. What we want to know is it a statistically significant difference? So the analysis of variance, or the ANOVA as we call it, calculates an F statistic, which is another one of these statistical tests where the higher the F statistic is, the more likely it is to be statistically significant. Basically what the F statistic tells you is only this. It tells you whether the difference between the mean for group 1 is different from 2 and 3, or whether 2 is different from 3 and 1. It just tells you that one of the means is statistically significantly different than the other 2. It doesn't tell you which one, of course, because it can't. It's just looking at all 3 of them. So, or all 4 or all 5, depending how many you have. So it basically just tells you one or more of these is an outlier from the other 2, and it's enough of an outlier that it's statistically significant. And the F statistic is, again, used to find a p-value. Now, if you can't tell which difference it is, then you have to do t-tests to figure out which one it is. So say, this is a pretty clear-cut example, but say you had like 8 things that you were comparing and the F statistic was statistically significant, what you'd have to do then is take the ones that were most likely to be different and do t-tests to figure out which one they were. And in a minute, you're going to hear about how the F statistic is calculated. And here's how the F statistic is calculated. To me, this is very intuitive. So it's the variance between the groups divided by the variance within the groups. Meaning, is the mean of group 1 compared to the mean of group 2, is that a bigger variance or a bigger difference than these standard deviations or the variance within the groups? And so the way that's expressed is the mean squares of the groups over mean squares of error, which is just a fancy way of saying that you look at the sum of the squares between the groups divided by the number of groups minus 1 over the sum of the squares within the groups divided by the number of total data points in the groups minus 1. The sum of squares, the SS, is the squares of the variance from the mean. And we talked about that on slide 8 when we were calculating standard deviation. So basically, the real thing about this formula is that on top, it talks about the difference between group 1 and group 2. And the bottom of the formula, the denominator, talks about the difference within group 1 and group 2. Okay? And so the intuitive thing to take home here is that groups with very high standard deviations are much less likely to be statistically significant. So linear regression, we're almost done, I promise, there's only 2 more. And these last 2 are very theoretical, so I'm not really even going to put numbers in them at all. Linear regression is used when the outcome variable is continuous. For example, the mean score on a test. So say that there were many potential contributing variables. This is a way to do multivariate analysis. For example, in the t-test example, when we wanted to look at students who came to class and students who didn't come to class, say we also want to throw other variables into the analysis, like the number of hours that they spent studying and their age and their gender, which I'm not at all saying that those things would affect how you would do on the exam, but everybody puts them in their study anyway. So say we wanted to look at those things. How would we look at the independent effect of each one of those things on the mean score on the exam? And the way that you do it is this. So these are slides that I got from the internet, and they're not the same example, obviously. The top one is looking at, the top left is looking at skin cancer mortality versus state latitude. But you can see that there's a slope equation there. Y equals something minus something x, right? And so what it's saying is that the y, which is mortality, is correlated with x, which is latitude, in some way. And that way is expressed as an equation, a slope equation. I'm sure you remember slope equations from algebra. And so Multiple linear regression, which is the box in the bottom right, shows you how to do that slope equation when you have lots of different x's. So each x is a variable. So x1 is, came to class, didn't come to class. x2 is gender. x3 is age. x4 is number of hours spent studying. Whatever else you want to look at, each one of those things winds up with a coefficient. And this is very complicated to do. And usually you use a computer program to sort of analyze the data points and generate some kind of slope equation for you. And so once you've generated the slope equation, those coefficients, those B1 and B2 and all of those, can get translated in a table into odds ratios that will tell you the independent effect of each one of the variables on the outcome. And there are different ways to do this if the exposure variables, the multiple exposure variables, some of them can be linear and some of them can be continuous and some can be categorical. There are ways to get around all of that. Just accept that it can be done. And if people really want to hear about it, they can come to office hours, but you definitely don't need to know it for the exam. So the sum up of this slide is just to understand that there are ways to model the independent effect of several variables on a continuous outcome, and it's usually expressed as a slope equation, which then gets translated into a table into odds ratios, and you decide whether they are statistically significant or not. Logistic regression is much the same as linear regression, but it's used when the outcome variable is categorical and can only have two possible outcomes, 0 or 1. So rather than saying, let's look at the score of the EPH exam, and I'm interested in all the scores, from 50 to 100, we're going to say, okay, I just want to look at who passed and who didn't pass. I'm just going to lump the students into two groups, right? And so logistic regression models the odds of the outcome being 1, not 0, when each exposure variable is in a certain form, and it controls for all the other variables. So again, it's a multivariate analysis. And so say, in our case with the EPH exam, that we wanted to model the odds of passing the exam. You could also model it on the odds of failing the exam. It depends on what you're more interested in showing. And then you'd be able to show, like, does coming to class make it more likely that you'll pass? Does being female make it more likely that you'll pass? Does being older make it more likely that you'll pass, etc. Usually, the way that you do this is you create a model for the equation, which it looks a lot like the slope equation for the linear regression, except that it's not quite that because it's not a continuous slope. And you'll just have to, again, now we're sort of in higher math, so take a deep breath, look at the flower. I'm not going to ask you to do this. I have to look it up myself. But just accept that it can be done. So the important thing about logistic regression, that when you read a paper that used logistic regression, what they will talk about is how variables were added to the model. And the important thing to think about here is when you're putting a bunch of multivariate variables into this model and saying, well, we want to look at how a whole bunch of things affect the outcome. You can't just put like every single one in there, because that junks up your equation and it increases the risk that you'll find something that's statistically significant, but it's really not true, just through chance. And so which variables you select to include in the model is an important step that's usually described in the paper. And there's three common ways to do it. One is a priori, just saying we think these are the variables that are important, and so we're only including these. Another way to do it is to start with one and then add another one, and then run the numbers, and then add another one, and then run the numbers with all three, and then add another one and run the numbers with all four. And the other way you can do it is put them all in to start with and then subtract sequentially in the same kind of way. And when you do a stepwise or sequential addition or subtraction, what you're looking for is, does the addition or subtraction of this variable change the impact of the other variables on the outcome by more than 10% usually. And so the results for each variable, the effect of each variable on the outcome, is expressed as an odds ratio with 95% confidence intervals. And if the 95% confidence interval contains 1, then that variable is not felt to be statistically significant. It's sort of the same as having a p greater than 0.05. So here's an example of the likelihood of having an MI after a year of being on simvastatin, which is a cholesterol-lowering drug. This is just a different way to think about the numbers in a study like that. So we're looking at a couple of populations of people, two populations, people that took the statin drug and people that didn't, and then we followed to see whether they had an MI or not. But we were also interested in looking at the impact of these other variables, exercise, and whether they took aspirin, and whether they followed a low-fat diet, and what was their gender, right? And so what you have to do, the results from a logistic regression are reported in a table like this. You list the variable, you list what value was modeled in the regression. So in this case, for example, we're saying that taking a statin drug versus not taking it changed your odds of having an MI versus not having an MI to 0.74. In other words, taking a statin drug made you 0.74 times as likely to have an MI, so less likely to have an MI, compared with people who were not taking a statin drug. And there's the 95% confidence interval, which again is 2 standard deviations on either side of the odds ratio. And so you can see in all these cases that since it's modeled on having an MI, most of these variables lower your risk of having an MI, except for being male, which raises it. And there will be tables like this in many of the studies that you read, so this is a helpful example to go back to. So just as a summary, and again, don't stress about knowing these formulas. I mostly just want you to understand what makes things more and less likely to be statistically significant, and in many cases it's sample size, and that's in your syllabus. Continuous variable with 2 groups is studied as a t-test, and the results are expressed as mean and standard deviation for each group, and the statistical measure that's used is a p-value. If it's a continuous variable and there's more than 2 groups, then analysis of variance is used, and it's expressed as a mean with a standard deviation, and the statistical measure is a p-value. If it's an ordinal or categorical variable, we use chi-square, and the results are expressed as, such and such percent of people in group 1 versus such and such percent of people in group 2 had the outcome, and it's a p-value. And then if you do multivariate regression with covariates, you have sort of 2 options. If your outcome variable is continuous, you can do it as a linear regression, and if your outcome variable is ordinal or categorical, you do it as a logistic regression. And the results are expressed as means or odds ratios, and the statistical measures are also there. So we will talk about this more in class, but the main point is just to have a general understanding of how this is done without actually, you're not going to have to do the calculations. Not even statisticians do the calculations. They have computer programs that do it for them. So I'm happy to be approached with any questions about these specifics, but again, it's more just sort of understanding if this goes up or this goes down, how does that affect the likelihood of statistical significance. All right, thank you for being patient. I hope you liked my flowers. They calmed me while I was giving this talk, and I will see you guys in class. Thanks.